Newton's law of gravitation. So what that means is like the Earth versus the moon, for example, or the Earth versus the sun, or like the space station orbiting the Earth. This talks about how those two things affect each other. The bigger the difference in the size of the two objects, then the stronger the force is between them. Like Earth is trapped rotating around the sun, and the moon is trapped rotating around the Earth. And are they fixed forever? The answer is no, they change a little bit, but given the size of these objects in our lifetime, there's no noticeable change in the way they affect each other. The formula here, F, that's the gravitational force between the two objects that's kind of holding them together. They attract each other, kind of like magnets. The G is this kind of universal number. Throughout the whole universe, it's believed that this number holds true. It's kind of like pi. It's a number like that. M1 is the mass. Mass is done in kilograms, not pounds. Pounds is weight. So the difference between mass and weight is I'm about 70 kilograms, whether I'm on the Earth, on the moon, or floating in space. Weight is when you take into account gravity. So on the Earth, I feel heavier, more weight than I would on the moon because the gravity is different. And then floating out in space, I don't know what that feels like, but I wouldn't feel my weight at all, but I'm still 72 kilograms. And so the amount of stuff I'm made of is mass. And we want mass here, not weight. And then the R is just how far those two things apart. So let's blow this up, screenshot it, and pick apart the numbers. Let's do it. So what we want to do is we want to apply this formula to the moon and the Earth. And the only difference really, the stuff that's going on down below, is since these numbers are so big, it's really going to be easier for us, instead of keeping track of all the zeros, is just use scientific notation like the first number here about the gravitational constant. So we're going to rewrite their distance and the masses in scientific notation. And then we're going to plug them into the formula and make that calculation for the formula. So first scientific notation, then formula, and we're done. So then we just have to carefully count here, and fortunately the commas are in there, so that helps. One thing, if we don't pay attention, is the distance between the Earth and the Moon, the 348,000, is given in kilometers. But in the question below, we're asked for meters. And then I just have to remember that kilo means 1,000. So for that distance R, I was asked about, I want that in meters. So 384,000, and then kilo means another 3 zeros to get it to meters. If I want to put that in scientific notation there, that means I want the decimal to be between the 3 and the 8. So that's 3, 6, 7, 8 places. So in scientific notation, this number right here would be 3.84 times 10 to the 8th power. And then M1, let's let that one be the moon. So let's write that one over here. And we want to write that in scientific notation. So the decimal needs to go between the 7 and the 3. So I would write 7.348 and then count by threes. So I'm just going to count the number of groups of 3. I have 1, 2, 3, 4, 5, 6, 7 whole groups of 3. 3 times 7 is 21, plus one more place should give me 10 to the power 22. Try to count by 3. Some days I'm good at that. 3, 6, 9, 12, 15, 18, 21, and one more place is 22. Okay, I think I did that right. you guys disagree with me, please shout out, let me know. So that's the mass of the moon in kilograms in scientific notation. And then let's do the mass of the Earth. We'll call that one M2. So how many places do we have there? We have one group of 3, 2, 3, 4, 5, 6, 7, 8 full groups of 3. 8 times 3 on a good day is 24. So I think that one would be 5.9722 times 10 to the 24th power. To enter that into this formula here, we just want to use parentheses occasionally. So anytime a number we plug in is complicated, more than just one number, like here I have a times in between, I want to put it in parentheses. So when I do that final calculation for the force, the R is going to have to be in parentheses. I think that's it, but we can always put extra ones to be safe. It doesn't hurt. So we could write this as parentheses, gravitational constant, 6.674 times 10 to the negative 11. And then that's times this fraction. So I'm just going to go parentheses for times, and then M1, 7.348 times 10 to the 22nd. And I always think it's a good idea to write down on paper what you're going to tell your calculator to do. Times the next mass, 5.9722 times 10 to the 24th. Close that one, and then divide by the radius squared. So since this is complicated, it's got to go in parentheses, 3.84 times 10 to the 8th, and then square it outside the parentheses. So that's the way I would type this into a calculator. So it's just a matter of carefully pushing those buttons to make that happen. So not too bad if we count carefully, read the fine print, double check I got all the right fine print. Let's see, meters versus kilometers, we fixed that. This says kilograms, that says kilograms. Kilograms, kilograms, we're cool there. Oh, significant digits. I can't remember if I've talked about that with you guys. In Math 62, I would have talked about it. So significant digits basically means look at the numbers you were given, ignoring any zeros on the right or the left. So left would be small numbers, right would be big numbers. And what's significant is everything but the zeros. So for example, this number right here has 3 significant digits, ignoring the zeros. This one has 4 significant digits. This one over here has 1, 2, 3, 4 significant digits, and this one has 4. When you make a calculation based on other numbers, the scientific rule is you can't have any more significant digits than the fewest ones you started with. And the fewest ones I started with were 3. So in my final answer, I'm only going to show 3 significant digits, and the rest I basically ignore. So let's see if we can type this in and agree on it. And I think I might need to split my screen for this to look at my numbers. Okay, I can kind of see them there. 4 in the denominator, and to the 1, 2, 3, 4, 5, 6, 7, 8. Is that right? I think so. Oops. I think I have that typed right. 3.84 times 10 to the 8th. Okay, so if I typed it right, I get 7.6270. So this is such a big number, my calculator automatically gave me scientific notation. Other calculators might look different. So if your calculator gives a different response and you're not sure what it means, let me know. 3 significant digits would be round to that 2 to a 3. So I would call it 7.63. So I think if I typed it in right, which is slightly questionable, that this would be 7.63 times 10 to the 28th power. I have a calculator at home that would have told me this was 7.63 big E 28. So some calculators give this notation, which means the E stands for the times 10, and the next thing is the power. So if your calculator says that, it means this. How's it going out there?
Good.
I think we missed something on the bottom part of that equation you did here. Your 3.84 times 10 to the 8th power squared, isn't it?
Oh shit, I didn't square it. I mean, oh shoot, I didn't square it. Thanks, Joe. Nailed it. Yep. All right, I get a different answer. Good job. So this would be 1.99 times 10 to the 20th. All right. Oops. That's the square. So it should be 1.99. Does that look better, Joe?
Yeah.
Okay. Good call. And again, the 3 places here was based on their idea about significant figures, which is related to the least number of significant figures we started with. All right, nice work, y'all.